So on Wednesday, we derived this result. So originally, it's conditional expectation given an event which occur on this positive probability. And we can express this conditional expectation by using unconditional expectation here. Okay. But we have to use the indicator function of the Fourier set E, right? Composite with the right normal value. So and divided by the probability of this event y long t. So that is the point. And this is the key result in our development of conditional expectation. Right? Okay, and here we can end up with this result under the condition that this expectation exists. So we have to prove that under what condition that this expectation exists. Okay. So here is the theorem. Again, we consider only discrete random values here, and we assume x as a finite expectation. It's quite standard assumption here. Then this expectation exists. Okay, for any Fourier set, and it's finite for any Fourier set. And again, the technique we use again and again is that if x has finite expectation, then the expectation of this positive part is finite, as well as the expectation of this negative part is finite. So usually we decompose the random value of x into two parts: the positive part and the negative part. So we have So now for any Fourier set B, we have alright. So because the value of the indicator is either 0 or 1. So if it's 1, of course the product does not change the value of x. But if the value is 0, then 0 times the value of random value of x will be, so as we know, okay, I think that's so obvious. And so that the positive part of this product will be less than equal to the positive part of x. Okay, this is of course. Similarly, for the negative part. So that the expectation of the positive part should be less than the expectation of the price. And the expectation of the negative parts, of course, is less than the expectation of the negative parts of x. And then the dot, which implies that the expectation is finite. So this is a very easy proof. Any questions? So always remember that a random variable has a finite expectation even only if its positive part has finite expectation and its negative part has finite expectation. Okay. Because we define, remember, we define the expectation of x by the difference of these two expectations. Because we know we can always compute the expectation of a negative random value. Okay. We know that. But the possibility is that such an expectation can have finite value or infinite value. So to prevent that this difference becomes to be undefined, we have to require that not both of them are infinite. So at least one of them should be finite. Okay. And in this case, we say that the expectation of x exists. But when it exists, the value is possible positive or finite or negative. It is possible infinite or finite or negative. So existence does not imply it is finite. Okay? But it is finite, then it implies that the expectation exists. Okay, so now we develop this theorem. Again, same assumption. X and y are two discrete random variables, and x has a finite expectation. Okay, then of course that a version of the condition expectation of x given y exists. We just prove this already. Okay, so in fact there are many versions of the condition expectation of x. And second point is that this expectation, okay, it is that the negative function of y, all right, times x, this expectation, can be equal to that we can replace x by the condition expectation of x given y. Okay. So that so it is the sum of y for the possible value b in the Fourier set. Okay. Okay, I will show you. And it is computable here. Okay, so we can compute that it is actually equal to the conditional. This is the conventional continuous expectation given this event, this atomic event, times the probability of the atomic event. Okay. And we only need to add on for all y, which is possible value and is also in the Fourier set. It's a direct formula from this, because this is a function of y together, right? It's a function of y, and again this is a function of y. So the product is a function of y. Okay? So to find the expectation of a function of y, of course we use the probability mass function of the discrete random variable. It's easy, you know. Expectation of a function of y. Suppose that. So let HP a Fourier measurable function. Function. Then the expectation of a function y is actually the sum of it's very easy. Okay. So it's just here. So now is h1 equal to okay. So now our h function it's 1by and this condition expectation. Or you can write it this way. Because I have given a remark before, this is actually is equal to okay. Okay. So this is a function so that we have now, but this is 1. This is 1 when only when y is in B. If y is not in B, then this is 0. So the summation can be specific to all y in B. Okay, and so now this is become 1, right? So we don't need to write this part again. So we have
Why can we write the indicator of the first one equals to
this one? So we have to prove that. Yeah, this is the difficult part. I just the easy part. Yeah. So it's quite. I want to know that this is just the from the elementary probability theory. This is what we have used such kind of expression in undergraduate study, right? I just wanted to point out that we have a product of two functions of y. So as a whole, it's a function of y. It's a function of y. And I just want to indicate that this function actually is this one is the indicator function times this function. Okay. Alright, so the crucial part is here. And before I prove that, there is a very useful formula. When the Fourier set B is taken to be R, because R itself is the Fourier set, right? So when B is equal to R, it is just equal to 1. Because Y is a real value, non value. So its value always in R. So this indicator one is just a constant one is 1. Okay? So if there is 1, we don't need to write it down. This is 1. Okay? And the Y is in R. So a special case is here. If we want to find if we want to find unconditional expectation of X, means just the ordinary expectation of X. The first, you can do it in 2 steps. First of all, you find its conditional expectation given y. Okay? And which is a function of y, so it's a random variable. And then you check the expectation of this random variable. At this moment, you may think, well, how come you want a two-step approach to find the expectation for y? Well, actually, you will have many examples that the two-step approach will be much easier than the one-step approach in many situations. Okay. So that this is a very useful formula. Yeah. And I just write down this expectation. So in many situations, it's quite easy to know the distribution of y, and then to compute the conditional expectation of x given this event y equal to 1. Because with the information, with the conditional information here, the conditional distribution of x comes to be straightforward in many situations. So it will be easier to compute this conditional expectation of x given y equal to beta y. So once we have the data, we have this, then it is easy to find this weights. So that's the key idea. Okay, that's the key idea. Any questions? Right. So there's no questions. So we have to prove this point. Now, by theorem, we know that because x has finite expectation, so we know that when this atomic event occurs with positive probability, right? Then this conditional expectation exists. It's a finite value, and so of course we know that we have a version of conditional expectation. So now for any Borel set B here, we check this expectation. So this is a function of y. This is a function of y, right? Okay. And what I have found here is just like here, right? So let's write down here. This one, and then. And then I specify that not only y is in B as well as also that that I just confine to rows y such that this atomic event has a positive probability. So this is some. Because now I want to express this conditional expectation by the traditional definition. So we know that this conditional expectation actually is here. Okay? So it is the conditional probability as a weighting to each x, each outcome of the random variable factor x. Okay? So before we do this, we have to make sure the denominator is positive. Okay? So that's why we specify that. Okay, and then we can cancel. Right? These two numbers here. Okay, so once we cancel these two numbers, it comes to like this one, much simpler formula, right? Okay, Now, because that in this expression, this probability will not be used in anything because we don't have a denominator, right? So we can just remove this restriction, okay, without affect anything. Why? Because that if we add those y such that the probability equals to 0, then this probability must be 0 because this probability is smaller than this probability. Smaller. So if this probability is 0, then of course this is 0, right? So when we do the extension here, we remove the restriction. We okay, I write down here. We get the same result, right? So the value does not change. And again, to write y without any restriction, we have to put the indicator function back here. Okay, so actually we just do the reverse process. So that so what is the definition here? Well, in this case, we regard this as a function of x and y this time, right? Because it involves x and it also involves y, right? So it's a function of x and y. And as this one, so suppose that h so let h be a parametric function right? Then we know h random variable, and when we take the expectation, okay, of this function, it is the double sum weighted by the joint distribution. So this is the joint with mixed function. Okay? It exists. This expectation may not exist. But if it exists, you have to compute that this way. So this is the traditional definition of expectation. So this time, the hxy actually, so now, here, the hxy becomes to x times indicator of 1. Okay? So the hxy, when we apply here, it's just x times indicator function 1. And then hxy come to x times indicator b of 1. Okay, so it's here.
When will it not exist? When will it not exist?
Oh, because that this h is arbitrary function. But here, I mean here in this theorem, maybe This is clear. And we have shown that this expression exists from the previous theorem. Just that.
Now, in that case,
Yeah.
in the upper proof, do you know whether it might exist?
Well, yeah. Okay. If you want to have an example, so let's say here. You can yeah. So let's say I write x equal to n, y equal to n. Okay. So I write. So we just take x and y to be let's say I give a description which is we know that this series has finite sum. Okay, so identity of the delta. Right? And I define the distribution to be okay. Let's type this one. Okay, and I let h to be so okay, and then x is y equal x, very special type of function. So the expectation of x is y is the expectation of x. Right? It's very simple. And so this is summation x. So it's n probability of, right? Because the possible value x has to be integers. So I just write it down. And so I plug in the distribution. So this is comes to, right? And this is input. Because sum of 1 over n diverge.
Why don't you put the equation of the triangle inside?
Oh, as a normalization. Because the summation of b should be equal to 1. So I have to normalize that, right? It's a normalization. It's a normalization. Well, but okay, this example is not a very good example because it shows you that probably I think maybe I write this way. Okay. Similarly, I think. 1, 2. So, okay. So this is the expectation So this for this function, the expectation does not exist. Right? No, they have the same distribution, but not identical. I just take this as an example. So they have the same distribution. So you can have two very different random values but have the same distribution. So it's possible that x equal to y is possible, but they may not be the same. Yes. This one? Oh, because h is Fourier measurable function. I indicated that before, right? Because it's Fourier measurable. For example, every continuous function is Fourier measurable. And also something like this one, I use Fourier set. It is also Fourier measurable. Of course, I encourage you to prove that, for example, this function is Fourier measurable by yourself. It's not difficult, especially because P is Fourier set. So this independent function must be Fourier measurable. Any other questions? Yes.
Not the conclusion for the past two equations.
This one. But yeah, well, just as I said, that this is a function of x and y, and this is the German's function. So this is just by this formula. It is exactly this formula. Up to now, I try to maintain the argument in very low level. So it seems like this is a very complicated one, but indeed it's just a function of x and y. Okay, so I have shown this identity. So remember, it's very useful whenever you want to compute such an expectation like this one. X times an implicator function y. You can replace the x by the conditional expectation of x given y. And remember, this conditional expectation of x, expectation of x given y is a function of y. And because it's a function of y, so this is come to, when you multiply together, this is a function of y too. So that's why we can compute it by the distribution of y only. It is marvelous because in many situations the distribution of x is quite difficult to know in many problems. In many problems, very difficult, really. Okay, but you can express this as a distribution, as a function of x of y. Then you can find find this number using the distribution as well. So you can find a random variable which is more apparent to you because it's easier for you to find the distribution one. So you should find a suitable one such that the distribution is easier to obtain. And then it is easier to compute this condition explication. Because whenever you given information y, the information x becomes to be much more easier to obtain. So it is called the two-step process, especially when we look at
teacher, what's the physical meaning of the double expectation?
Oh, this double expectation?
Yeah.
Oh, actually, because the expectation is for a random variable, right? Yeah. And okay, so this the first expectation is the expectation of this random variable. So the expectation of this is not a conventional expectation; it is a random variable. But we use this notation. So it's a random variable, and this random variable is a function of that.
So the first expectation is
It's an ordinary expectation. So the result is a scalar. It's a real number. But this expectation, and I use this one, is a random variable. It's not a value. Why they are equal? It's because that I just proved this is equal. Okay. And this is just a special case of this general formula when B is taken to be the whole set of real numbers, the R. Mathematics is a logical structure. So I had to do definition, lemma, theorem, corollary. So every step should based on the step in the previous paragraph or previous sections. So it's a chain reactions. You have to understand all the concept and results during the process. Other questions? So you know, when I define the condition expectations, I introduce this function h to embody all the information about conditional expectation of x given y, right? Because remember, that at the beginning of this section, I introduced the traditional definition of conditional probability. It is quite straightforward and intuitive, right? It has been used in elementary probability. So once we have conditional probability, we can define conditional expectation of a given this atomic event. And we require this atomic event has occurred with positive probability. This is the requirement, right? Because that we have to put it into the denominator. So we must assume this condition is true. And so we have this one. Okay? And so given the little y, you can have a number. Here. This is a real number. Alright? It's called the conditional expectation of x given this atomic event. And we embody all this information for arbitrary y, okay, as a function. Here, okay? So now we create a function h, okay? And so for each y, alright, the function value is just the traditional conditional expectation of x given the atomic event. Alright, but there is something not complete. The something is that what about that this atomic event is 0? So we have arbitration. So we have to do some assignment. So that this arbitration so here these are two frequent assignments used in degree theory. One is assign the expectation of x if it exists, or just assign 0 or something like that. Right. So the only thing, the point is that this function embody all the information about conditional expectation, and that h is measurable, is Fourier measurable. And so that we define a new random variable, okay, which is a function y. And this random variable contains all the information about conditional expectation of x given y. So that's why we give a name here. We give a name here. So if we call it conditional expectation of x given y with this notation, but when we look at this notation, it is come to a function y in this context. In this context, okay? So it's a function. Okay, so the composition is this way. First of all, y we know is a function from the sample space to the set of real numbers. Okay, and once we have these real numbers, we activate the parametric function h, so that what we get is this conditional expectation.
So we can consider the conditional expectation as a random variable.
Altogether.
Yeah.
Yeah. So that's why this is my creation. It's a construction. It's a human-made thing. Okay, it's a human-made thing here. And this construction becomes very useful. This is what I want to develop the whole theory. And the very last theorem is just the beginning. Okay, it's just the beginning. This construction gives you a lot of inconvenience, and it is a very powerful tool in the modern study of stochastic process and in the study of modern probability. All right, so this is key because that in the whole semester we will use these notations quite often, and this one will help you to solve problems, especially not only in chapter 1 of the textbook, but also in other chapters.
Oh, so Peter,
Yeah.
if we have multiple chain, we have multiple.
It's a composition.
Yeah, it's a multiple composition. And so we need the multiple expectation to get the output or the sample space.
Well, yeah, because the reason why we compose the random variable y with stitch h, it is because we know that when we define the function h, actually we look at the random variable x from the point of view of y already. So this is the frequent meaning for conditional expectation of x given y. It's a kind of indirect way. Right? If we want to know the expectation of x, this is our purpose. Sometimes we need to to see from the angle of y. So in many situations, we just say given a situation. So given y, so given an observation y, which has a value little y, then we want to know what is the expectation of x. And if from time to time, this angle give you a very easy way to compute this condition expectation. It's much more easy. Okay. So so because this is from the angle of y. Now, so when we want to construct or to establish a random variables to embody the angle of y. Alright, so we should composite the h composite with the y, because this is for the angle of y. So it's quite natural. Right? So that whenever we have an outcome, by the measurement of the device y, we get a value. Alright? So we put the value here. So we now have a stance of the y. Under this stance, we can compute these conditions. So it's a story. It is a streaming, natural streaming for that. Because if you composite with other, like if you h come with x, then this story will be distorted. There's no connection between x and this one, because the condition expression will compute this from the angle of y. So the feeling is that, what is this object? What is this object? You can think about this is the picture of x through the viewpoint of y. And it's the total picture of x, because it's the expectation. Right? So a total picture of x given from the angle of y. And y can be arbitrary value, right? Because y is a random value. Right. So the total picture through the angle of y is also a random phenomenon. So that's why it's a random value. In signal processing point of view, it's a kind of data processing. A kind of data processing. Right? Because it's a function, right? So that the angle of y through this data process h give you a picture of the x, the total picture of x. And this is a predefined function. Okay? So, not many things you need to look at over and over again, but in this period, maybe in 2 or 3 weeks, you have to read from here up to to understand the definition of h. Okay, and then the transition. And then you will appreciate this definition after we prove several theorems later. And so one of the theorem is here. Okay, this is the first basic state we have. So once we have correlation this kind of relation that so and we can replace x by from the angle. Even more here. To know the expectation, we can do it. First of all, to know the expectation of x through the angle y. All right, and then we take the expectation of this function y. As a function of y, so that we can compute this expectation by the distribution function of y. Question? Okay. Fine. So now here is the corollary. So consider two discrete random variables x and y, and if x has a finite expectation, then this one is condition expectation of x given this event. Right. Given this event can be done by what? By replace the x by this condition expectation of x given y. Because you are asking expectation of a given an event defined by y, right? So that's why that means that you want to know the total picture through an event defined by y. So it means that through the angle y. So it is equivalent that you can replace this totality because this is the whole information about the total picture of x given the detailed observation of y already. So this is the most detailed angle, the things you can have. Okay, so you can replace this random value by this new random value, and which is just a function of y. And then when you are conditioned on an event defined by y. So it is a replacement. It is a replacement. And this replacement reduces the difficulty of the problem. Okay, so this is a corollary. It's a simple corollary. Okay, so let's take a short break for 5 minutes. A great study. The material is usually taken from 19th century, 18th, 19th century. So it's called the classical map. The point view I put here is a modern view developed in the first half century, in the first half of the 20th century, around World War II. Okay. Some has been developed after the Second World War. So it's quite modern. But with this development, mathematicians are able to investigate difficult problems in stochastic processes. So it's kind of a language, and I just ask you to be used to that language. Alright, so now we go to next steps. In the previous material, we consider two discrete random variables because discrete random variables are much more intuitive. So now we consider x and y be two jointly absolutely continuous random variables. When we say that two random variables are jointly absolutely continuous, right. Then let me define absolute continuity for a single random variable. Right. So we say a random variable x is called continuous. CDF. So a random variable is called a continuous random variable if it's CDF, right? Or sometimes people say it's a probability discrete function, but more frequently people call it cumulative distribution function, CDF. And this CDF is a continuous function of x. Okay. So for example, right? So if you have if the CDF of a random variable x like this one, then we know that this random variable is a continuous random variable. Now, a random variable x, all right, is called absolutely continuous. Okay. All right, so a little bit different. Now, I put absolute, one more word before continuous. So we say if there exists a function such that one the function is an interval. And I is integrable. First of all, it's non-negative. Second thing, it says that the CDF of x can be expressed as an integral, and this is called the indeterminate integral of this function. Oh, sorry. I'm sorry. Okay? In this case, f of x is called probability B density function of x. Okay, so it's called PDF. Any questions? Yes. Give an example. Okay. Okay. Before I give an example, okay. Example first. Okay. So let x be a random variable with a CDF okay. So x is a random variable. Okay, and for x less than 0, the CDF has value 0. Yeah. And for x greater than 0, so when x is equal to 0, 1 minus 1 is 0. Right? And then, so we will have one exponential function. So this comes to and so now we take f of x to be 0 and okay, so this take this function. And what is this function? Can I erase this? Okay. So it's not a continuous function, right? But it's continuous except at x equal to 0. So it has a jump at x equals 0. But this function is Fourier matrix, and also is integral. So now I will show, of course, so we check for x less than 0. 0 is, so fx is 0 by definition, right? By this definition. And this is 0 because it's all 0 here. Okay, up to x, so the x is here, all 0. So the exception, right? Yeah, and then it is. It is obvious that this function is non-integral. Now we have that. Now for x greater than or equal to 0, then we integrate x. Right? We do the integration. And the integration, because x is greater than or equal to 0, and because that the function f of x is 0 less than when x less than 0, so we can start with 0 x. Is that okay? Fine, right? It's crucial to put 0 here. You will see. And this is right? Okay, and by antiderivative, we have right? Okay. And the result 1 minus, and this is equal. So we prove that when x greater than or equal to 0, this integral is equal to the CDF, the value of CDF at x, and this is true. So that's the conclusion. Absolutely continuous. And fx is a PDF of x. Right? So prove that. Now, from this example, I showed you that PDF is not unique. Why? I define another g of x. Okay. So this time my definition is here. I want the function has value 0 when x equals to 0. And then I have so this function is different from this function at x equals to 0. So they are different. But you can see that we also have this result, right? We we have this result. And we know g of x whether is non-negative. So again, g of x is another PDF of x. Right? Another PDF of x. So, but x and g are different functions. Actually, f and g are equal almost everywhere, okay? Because they are equal almost, except a point. Even though they are different at one point, they are different functions. They are different functions. So, so that's the example. Any questions? Mark. 1. An absolutely continuous function, a continuous random variable. Infinitely many PDF. Second, second is an absolutely continuous random variable must be continuous. Why? Because its CDF can be expressed as an integral, and then it must be continuous. It's very easy to show it by figures. Okay? Maybe I didn't think. So, absolutely continuous random variable is more restrictive than continuous random variable. Okay? Because it has probability density functions. Not every continuous function has a probability density function. Okay? So you know that. Okay, so when we understand the absolute continuity, right, for a single random variable, now we can define two random variables. We say two random variables are jointly absolutely continuous. With joint, we want to know they are joint. So they are jointly absolutely continuous random variables with a joint probability density function. Right? If okay, I think this one, this definition is much stronger. Right? So so actually, right. We usually ask for, of course, the probability must be non-negative. And the function is Fourier measurable, so that we can do the any parametric function, okay, will be integrable if it satisfies this expression. I think so. So that for any two Fourier set, that this is true. In particular, I think let me give a traditional definition for that. Okay. Before I erase all the material on the blackboard, do you have any questions? Okay, good. So. The joint unity distribution function of two random variables x and y is defined freedom. We know that before, right? So this is a traditional definition of joint CDF of x and y. So it is just the probability of this joint effect. Capital X less than equal to b for x, capital Y less than equal to b. So this is x and y are called jointly absolutely continuous if there exists an integral form. So now I put it more specifically that there exists a Fourier measurable function mapped from R2 goes to R such that first of all, f of xy greater than equal to 0 of xy are set. Second, fxy, the joint CDF can be expressed by double equal x y u v e okay. So we can express them this way. So this definition is parallel to the definition for joint continuity for a single random value. So now here is for two random values. And we call these two random values are jointly absolutely continuous. And then if this is true, then this f in this case f of f is called joint validity density function. So this is the situation. Now remark. The probability of this joint event, as our definition, is just a joint here, right? And because it is joint absolutely continuous, so that is equal to so this is actually equal to probability of x okay. So this is another expression is that x belongs to this Fourier set. Okay, from minus infinity to x, y belongs to this Fourier set. And this one right? So this one cannot be because this one are jointly absolutely continuous. And so that so this is another expression is like this one. Alright, it's here. And by definition of this joint there is here. And from the joint absolute continuity, we have this double integral. So we establish for this particular Fourier state, x in this particular Fourier state, y is in this particular Fourier state, we just double integral over this Fourier state, over this Fourier state. This is just the expression. And actually, this definition implies here, the fact here, that these two spatial kind of Fourier set can be extended to arbitrary Fourier set. Okay? So x in Fourier set 1, y is in Fourier set 1 is equal to the double integrals. So for x we over x1, so little y we integral over u2. For example, if x is in from A to B, y is in C to D. Alright, so the x will integrate from A to B, and the y from C to D. From C to D. Alright, and so this is we come to a definite integral, double integral. So you have so this definition is actually you can regard this is a theorem. Okay, but conversely you can use this as a definition. So this definition is much more stronger. So we are considering the situation that we have two quantum variables, and they are jointly absolutely continuous. Means that they have joint PDF. So that they are joint probabilities. Because the spin function, joint CDF is just a special kind of probability like this. A special kind. And it can be expressed as an integral by this joint PDF. So the evaluation comes to this evaluation. And quite often you know how to do it. It's your experience in calculus. Okay. So now with joint PDF we can define marginal PDF. So the marginal PDF is that for any y such that this is positive. Okay. So we can, let me ask you, if you have a joint PDF, you know what is marginal PDF, right? Do I need to give you definition? If you need, just raise your hand. So, right. So for example, the marginal PDF of y is by definition is this integral. Okay, this integral. Alright, so if we integrate over x. Similarly, we know fx, we can have a marginal PDF of quantum variable x. So now, suppose that we have a situation that for y, this integral is positive. Now we define the conditional expectation of x given y equal to little y. Right? So this is a definition from elementary probability theory you encountered in your undergraduate study. So this is just a definition. Say I put a triangle. So that because this is defined to be the conditional PDF of x given y. Right? So this is actually our conventional definition. So the conventional definition of that is this. And because we have to put the marginal density function y here, so we have to make sure that this is positive. So for any y such that the marginal density of y given is positive, then we can define conditional PDF of x given y by this ratio. So this is the definition. And so that then we take the average. Right. So this is the definition for that. And of course, provide this is we can have this definition provided that the integral exists. So we need a theorem to make sure that this is a finite number, right? And similarly, we have this parallel theorem say that suppose we have two quantum variables who are jointly absolutely continuous. So they have a joint period. And suppose x has a finite expectation. Okay, so now x has a finite expectation. Then the conditional expectation of x given y equal to x, given capital Y equal to little y, exists and is finite for almost all y. Okay, with this within zero. The reason why we put for almost of y is that when we integrate, so when we do the integration over over all the y such that the value is positive. But this is the same as no restriction. Because when you include the y such that this function value is 0, you will not change anything. So this is equal to 1. So that's why we call it almost a y, because that the y such that this is positive when you add them together, the density add them together. Okay, so what is that? The probability is that indicator of this event that so this is the probability of this event is equal to 1. So from this event, so we said it is for almost all that so this is constant. This is final expectation exists at this final value. Okay. So the proof quite similar to the proof we have done for discrete random variable. Okay, again, we use this graph. X has a final expectation if and only its positive part has final expectation, and this negative part also has final expectation. Okay, and so now we compute this final expectation. I'm sorry, to compute the expectation of the positive part of x. So that we just integrate over, because this is a PDF, right? And PDF, so x here. Now, and we integrate over all x greater than equal to 0. Because we just do the positive part. And by definition, the marginal PDF it can be computed from the joint PDF. Right? Integrate over 1. Integrate over 1. Alright, and now we exchange the order of integration. And it is possible because the integral is non-negative. Because we are doing the x along the region that x is non-negative. And we know joint PDF is always non-negative. So the integral is non-negative. Okay, has non-negative value. And so we can exchange the order of the integration. That is again a probability theorem, very general theorem we can use. Alright? And again, that we restrict the y such that the marginal density has positive value. And this will not alter the value because that if this function has 0 value at y, then the corresponding film period should be 0. Okay, so go over here. So this integral, right, must be 0. And so this implies that for the given y, because y is given, right? Given. And so this as a function of x is 0 for almost all x in the real line. So we have no effect. And so that we can put the divide and multiply the same marginal function. And the reason why we can do this is we work on all y such that this marginal function has positive value. So we can do so. Okay? And so, because this is, as we know that this equation is finite value, so that this integral is finite value. When this integral has finite value, then the inner part, this part, must be finite for y, right? For y for Fourier set. Such that whenever y in this Fourier set, the integral is finite. Because that if in this set, in this set, we know this set. This set. But when y in this set, then just as I find here, the indicator of this event. Sorry. I think. Sorry, I think I have to say y. I think I just put the event here. The f of y not equal to 0. So this integral should be finite. Because this integral is a function of y. It's a function of y. So this integral must be finite with degree 1. And similarly, this integral when we yes. Oh, sorry. But I have to finish. Just stop here.